We can also charge objects by induction, which means we don't have to make physical contact. What we could do in this case is take our positively charged rod, and now our metal sphere is connected to what we call ground. This could be the literal ground, it could be the Earth, because the Earth is an infinite source or sink of electrons. We can put as many as we want in it or take as many as we want out of it, at least on human scales. So if we move this positive rod towards this grounded sphere, what we'll see is electrons will run up from the Earth to this side of the sphere to get closer to the positive charges. And we'll have positive charges left over on the other side of the sphere. Now, if we were to move the rod away, then the extra electrons would run back down the wire where they came from, and the sphere would go back to being neutral. But what if, while the rod is still in place and these extra electrons are running around in the sphere, what if we cut that wire so they can't get back down to to the ground? Now we can move the rod away and we'll leave this sphere negatively charged because we've imported these electrons from the Earth and then we cut off their only way to get out. This is charging by induction. Once we get these things charged, what we can see is there is an attraction or a repulsion between them. And it turns out that the actual form of the expression that tells us how strongly they attract or repel each other is exactly like what you saw for Newton's law of gravity last semester. If we write our charges as Q1 and Q2 and we say the distance between their centers is R, we get that the force between them is K Q1 Q2 divided by R squared. This is called Coulomb's law, and K is the constant that tells us about how strong the force is. In metric units, MKS units, K is 8.99 times 10 to the ninth Newton meters squared per Coulomb squared. If you look at the units on K, you can see that's what they have to be because we have to end up with newtons. We have to get rid of meters squared on the bottom and Coulomb squared on the top. Compare that to Newton's law of gravity, which is F equals G m1 m2 over r squared, and you'll see they look almost identical. One difference is since gravity is always attractive, we just remember that. But we can use the idea that a negative force is attractive and a positive force is repulsive, and then the signs of Q1 and Q2 will take care of whether something is attractive or repulsive for us. For example, we can look at the relative strengths of gravity and the electrostatic force in the hydrogen atom. We can look up what's the average distance between the proton and the electron in the ground state of hydrogen, and we get this tiny distance, about 5.3 times 10 to the negative 11 meters. We look up the masses for these two particles, and we can find the force of gravity between them, and of course it's microscopic, 3.6 times 10 to the negative 47 newtons, which is unimaginably small. What about the electrostatic force between them? What changes here is now the masses get replaced by charges, which are identical, except for the sign, and the universal gravitational constant G, which is pretty small here, is replaced by K, which is about 20 orders of magnitude larger. We put in the numbers, and for electrostatics, we get negative 8.2 times 10 to the negative 8 newtons. Still very small, but realistically, the ratio of these things, and we should ignore the sign here because this would be negative as well, the ratio of these two strengths is 2 times 10 to the 39, which is just unimaginably large. To compare it, the universe is believed to be about 10 to the 27 meters across. So if we look at the ratio between the size of a hydrogen atom, which is the smallest thing we might encounter in chemistry, and the largest thing we can imagine, that's a factor of about 200 times smaller than the difference between the forces in the atom. So gravity means absolutely nothing to the structure of the hydrogen atom. And that's why we say for many purposes, gravity doesn't matter at all. Why does it seem like it matters so much to us? Well, there's two reasons. One, almost all matter is electrically neutral, which means the much stronger electric force cancels out. We don't feel an electric attraction between yourself and your desk. You do have a gravitational attraction between them, but it's incredibly small because the mass of both you and your desk is incredibly small. The other reason gravity wins eventually is it's always attractive and there's never a repulsive component. So every single particle of you is pulling on every single particle of the Earth. And there's nothing to cancel it out. So that's the reason you're pulled down to the surface of the Earth. The electrostatic force doesn't come into it because you have positive and negative charges in your body, and so does the Earth, and they're all balanced. So gravity is really the only force left over for us to notice, and we only notice it when there's lots of mass, like the entire Earth.